I think it's just possible that there really isn't any quantum mechanics at all. It's just a manifestation of classical physics that has not been recognized. This is a major discovery in Newton's theory of gravity, only 4 years old. This is probably the most important symmetry in physics. This is why I think we may have stumbled on the nature of creation.
Physics traditionally builds from notions of time and scale. However, today we have a treat with British physicist Julian Barbour, who argues that the universe is grounded fundamentally in relationships between particles, and this upends even the primacy of wave functions.
All the evidence can in principle be explained without any wave function.
Discarding external clocks and rulers, Julian develops something called shape dynamics. This is where instantaneous configurations, or snapshots, are primary.
My conjecture now is that the whole story is incredibly much simpler than anybody thinks.
Ordinarily, we rely on concepts like entropy increase and the past hypothesis to explain time's arrow. However,
the second law applies to systems in a box. If the universe is not in a box, all bets are off.
This relational view implies that quantum mechanics comes from the statistics of the ratios of the shapes between particles.
Nothing but ratios.
You said that you have some radical ideas that you've developed recently with your main collaborator about the structure of creation. You're going to speak about what that means. You also have some ideas on consciousness and some new ideas about how quantum theory needs to be interpreted without reference to wave functions or Planck's constant. Please explain what all of that means.
Right. Well, leaving actually, just about quantum mechanics, I think it's just possible that there really isn't any quantum mechanics at all. It's just a manifestation of classical physics that has not been recognized. But let's come to that because we need to build up to it step by step. All of this has come from, in fact, it came from a very standard idea that's been doing the rounds in attempts to create quantum gravity for 60 years, nearly 60 years, when the famous Wheeler-DeWitt equation suggested that the quantum universe was completely static. There were just probabilities for different configurations. If you had the simplest model universe of 3 particles that would form a triangle, according to the Wheeler-DeWitt equation, you would just have probabilities for those triangles and nothing less. Now, I've been thinking for a long time, it's nonsense to say if there's just 3 particles that they have a triangle which has both a shape and a size, because a size assumes that you've got a ruler in addition to the universe. If the 3 particles are the whole universe, it's ridiculous to say that there's a ruler in addition to measure its size. So you must think just purely in terms of its size. Its shape. So my idea was in this idea with the Wheeler-DeWitt equation, people had been thinking that there's no sort of change overall, but what happens is part of the universe looks, if you look you can see, as I move my head is moving relative to the background.
Mm-hmm.
But you could have lots of snapshots where my head is in different positions relative to the background. So you would have a heap of snapshots. My head is there in different positions relative to the background. And then they would say that my head is the hand of the moving clock. And that tells you what the rest of the universe. So you'd have to have pictures with the rest of my room looking rather different than it is with just that beam behind me. So this was called the internal time idea. And people have been putting it forward, different versions of what they would propose. Now, none of them had chosen something which was scale invariant. And it was always a bit invidious. They were choosing out one part of the universe to be the clock and the rest to be the rest of the universe. So then I suggested, well, first of all, it should be something which is doesn't depend on size. It should be scale invariant. It should be just something that depends upon the size, the shape. And let's see what's happened. So you can consider, I introduced a long time ago the notion of shape space. So if you have three identical particles, their shape space, it just consists of the complete set of all the shapes that those three particles can make. There's one distinguished, which is the equilateral triangle, and then they get more and more pointed. So there's one particle here and two, and they get further out like that. So I suggested that quantum theory, the time of quantum theory, should be something which measures that quantity. And that quantity turns out to be very, very interesting. And when my collaborator, so I wrote down, I proposed a time-dependent Schrödinger equation where that quantity is the time. Now it's scale invariant, so it can't have a Planck's constant because Planck's constant has got dimensions. It's got the dimensions of action. So that would mean already that Planck's constant would have to emerge out of the theory.
Sorry, what are you trying to measure? You said you're trying to measure that? What's the that?
This quantity, something that would be scale invariant. Well, I wonder, why don't we actually look at the on page 1 because there's a formula there which would.
Sure.
Well, first of all, this is very, very interesting. A lot of this has come from me reading Leibniz back in 1977, and Leibniz said, if there was no variety in the world, we couldn't say anything. We couldn't see anything. We wouldn't exist. I mean, you can see me talking because there's variety. There's a lot of different structure in my head and behind me and things like that. And so Leibniz elevated variety to the maximum, most important thing that you could have in anything. And it's surprising how few people think that way in theoretical physics.
You mean to say that in order for you to perceive something or in order for something to exist, there needs to be difference?
There has to be difference, yes. So I'm calling it variety. And so so then the question is suppose the universe just consists of point particles or points, and they exist in space. So then, given those points distributed in space, what is the simplest scale invariant number which characterizes the extent to which they are distributed or uniformly clustered? So, that's the first thing. I mean, think about looking at the stars at night. I mean, wonderful if you're in Arizona or somewhere and you can see, there's the constellation of Orion. It's a distribution of stars and it stands out. There's variety there. And then there's large stretches of the sky where there's not much variety. And then the other ones where there are. So then the question is, can you express that mathematically? So in Euclidean space, suppose there are just three particles. Now, here's my definition for variety. So they are the separations between, let there be three particles, and let the separations between them be A, B, and C. Now, square all those separations, and you can make as many as you like. You just go on adding more, however many separations you've got. And you take the square root of that, and then you multiply it by the sum of 1 over A plus 1 over B plus 1 over C. Now, if you look at that expression, clearly if you multiply everything by X, so everything in the square root, you multiply by X, so that makes it X squared. So you can take the X squared out and it becomes X on the top, and then you do the bottom the same with the ones on the right, and you get an X 1 over X. So you get X over X equals 1. So that quantity has not changed. It's scale invariant. And this is really, to me, amazing that, as I say, this quantity emerged in Newton's theory of gravity in a special situation when in the Newtonian terms, all the particles collide together. But in reality, what's happening is the shape is becoming an equilateral triangle. That's the most interesting case. It can also happen if they're all on a line, but it's a very special shape. And that's the only case I know in the whole of theoretical physics where something which does not depend on scale plays a role. And I've increasingly come to think this is probably the most important symmetry in physics, far more important than the Lorentz group and all the other things that seem to be so very important. And it's really fascinating what that number does, that pure number there. It's such a simple number. And Leibniz wrote a famous little book called The Monadology in 1714.
Well, time doesn't exist, so it could have been 1900s.
Yes, that's right, yes. But duration doesn't exist. I would say instants of time exist. They are like the images on a pack of cards or something like that.
All right.
Stacked, like we showed that last time we spoke.
Yeah, and just for people who are wondering about the last time we spoke, it was a video that went quite viral, actually, especially for how in-depth and technical it was. And I'll place that link on screen and in the description.
Yes. So Leibniz talked about looking at a town from different points of view, and he says they all look different, but there's really just one town there, seen from different points of view. He says they're multiplied in perspective. And then he says, this is the means of obtaining as much variety as possible, but with the greatest order possible. And he certainly didn't have that expression that I've got there, variety, the one that I've just described with the square root and then the thing that multiplies it. But I think this is you could make many more like that, but this is the absolute simplest one you can choose. And in fact, there's 2 or 3 really fascinating things about it. One is that when you really look at Newton's theory, so Newton introduced these concepts of absolute space, absolute time, absolute space, and with absolute space goes the notion of an absolute scale, that there is a ruler outside the universe. When you get rid of those things which Newton added, and you just keep his notion of the gravitational force and his second law of motion, what you find is that the real core of Newton's theory for 3 particles is just that quantity that I've called variety there. It comes out of saying, well, there are points in space, just like there are stars in the sky, and lo and behold, the expression you use to characterize their distribution is right at the heart. It's the beginning and end of Newton's theory of gravity. Isn't that pretty surprising for a start? And then even more remarkable, and this was a discovery that was made about 4 years ago. This came about because I've been talking for many years to a professor at the observatory in Paris about Newton's theory of gravity. And particularly because there are Newtonian Big Bangs.
What do you mean?
So back in 1907, a Finnish mathematician called Sundman asked in Newtonian terms, can all the 3 particles, so there's a 3-body problem, that's 3 particles interacting with each other, can they all collide together at a point? And he said, nobody's asked this question before, but I'm going to prove that they can. And what he meant by that is that quantity that's the square root vanishes, that one that is the sum of the things, that square root would vanish, because that's the quantity which measures the size of a Newtonian 3-body universe, 3-particle universe.
Why can't it trivially vanish in the equilateral case that you mentioned as long as the masses are the same?
They can in an absolute space, but if they start off and you imagine they've got a certain size, this is why it is so difficult to shed a lot of preconceptions that are sort of built into us by our experience, the way we live on the surface of the stable Earth. I mean, I come into my study, you see it behind me, and it always seems to me the same size. Now, it's the same size relative to me. The ratio of the sizes doesn't change, and that leads us to believe that sizes are absolute. But it without all the evidence from the universe around us and in the first place the world around us, we couldn't say something like that. So if you start and you imagine that you've got an equilateral triangle of a given size, you make them the size vanish by bit, bringing the points closer to each other. But it still stays as an equilateral triangle. So however small you make it, it stays an equilateral triangle. Now, what it turns out in Newton's theory of gravity, when you try and do that, imagining that this quantity in the square root, under the square root, it's the square root measures the size, you find that Newton's equations stop. When you get to the equilateral shape, the equations don't work any longer. You can't go any further. So, and this was discovered in 1907. And there's a special condition. They can't have any angular momentum. They can't be rotating at all. But then, in Newtonian terms, if you run that the other way, what happens is that then the shape changes. So it starts off equilateral, and then the shape changes and becomes more and more pointed. And in fact, then you find that two particles start going round each other, and the other one goes off in the other direction. So things start happening. But that's really a Newtonian Big Bang. It starts with the equilateral triangle. That's the first instant of time. And then things happen, so to speak. You go on there. So that's all very interesting. Now this is 20 years, 2 decades before Hubble discovers expansion of the universe, but it's sitting there in Newton's theory, and that equilateral triangle is in some very real sense the first instant of time. After that, things happen. Now, and moreover, then a year later, it was shown that can happen with an arbitrary number of particles. You can have 1 trillion particles. They can't all start off as equilateral triangle, but they will start off with a very, very, very uniform shape. Won't be completely uniform. It'll be somewhat like the one on the left-hand one at the bottom of the illustration that I'm showing there.
So the bottom left would be akin to the FRW universe?
Well, no, Friedman, Robertson, Moore, you see, that I would say cosmology is very, very suspect. I've been discussing this with 1 or 2 really top cosmologists, because there's no variety in it at all. It's completely washed out. And they do actually quite struggle. So all of modern cosmology relies upon something called inflation and quantum effects while inflation is happening. Now, in part, it works remarkably well, but it's all a bit ad hoc, and people don't quite know how it starts. Now, the great joy about the Newtonian theory is there's always variety there. And it will form structure. So that was the great problem with Friedman, Robertson, Walker in general relativity. How on earth does the structure form?
What I mean to say is, if you take a look at the bottom left one, that one looks like the homogeneous universe that's isotropic, whereas the one on the right is what characterizes people's experience when they look up at the galaxies and the stars. Just a moment. Don't go anywhere. Hey, I see you inching away. Don't be like The Economy. Instead, read The Economist. I thought all The Economist was something that CEOs read to stay up to date on world trends. And that's true, but that's not only true. What I found more than useful for myself personally is their coverage of math, physics, philosophy, and AI, especially how something is perceived by other countries and how it may impact markets. For instance, The Economist had an interview with some of the people behind DeepSeek the week DeepSeek was launched. No one else had that. Another example is The Economist has this fantastic article on the recent dark energy data, which surpasses even Scientific American's coverage, in my opinion. They also have the chart of everything. It's like the chart version of this channel. It's something which is a pleasure to scroll through and learn from. Links to all of these will be in the description, of course. Now, The Economist's commitment to rigorous journalism means that you get a clear picture of the world's most significant developments. I am personally interested in the more scientific ones, like this one on extending life via mitochondrial transplants, which creates actually a new field of medicine, something that would make Michael Levin proud. The Economist also covers culture, finance and economics, business, international affairs, Britain, Europe, the Middle East, Africa, China, Asia, the Americas, and of course, the USA. Whether it's the latest in scientific innovation or the shifting landscape of global politics, The Economist provides comprehensive coverage, and it goes far beyond just headlines. Look, if you're passionate about expanding your knowledge and gaining a new understanding, a deeper one, of the forces that shape our world, then I highly recommend subscribing to The Economist. I subscribe to them, and it's an investment into your intellectual growth. It's one that you won't regret. As a listener of this podcast, you'll get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/toe, TOE, to get started. Thanks for tuning in, and now let's get back to the exploration of the mysteries of our universe. Again, that's economist.com/toe. What characterizes people's experience when they look up at the galaxies and the stars?
Yes, but in fact, if you could see it, why don't we, actually a better one, why don't we go and look at page 3? On the left, this is again equivalent to the first instant of time, and you'll see on the left, this is 5,000 particles, an incredible spherical ball. And that's unique, this extraordinary spherical ball. It only happens exactly with Newton's theory. And then on the right, there's an equatorial section through it. And you'll see, although it's very uniform, it's not perfectly uniform. So Newtonian theory is completely lacking that appalling problem that they had in cosmology with Einstein's theory, which starts the Friedmann-Robertson-Walker model, which has been the backbone of cosmology for 60 years or more, 80 years.
When you say that people here are looking at particles are usually defined with respect to some space-time symmetry. So, for instance, an electron is like a certain irreducible representation of the Poincare symmetry. So what sort of particle here is there if you don't have space in order for you to even have space-time? How are you defining particles?
I'm just using Euclidean space. Euclidean space you can have points separated by Euclidean distances.
Okay, so these are just points in Euclidean space, and you're calling those points particles.
Let me. I think what I'm now arguing is that it's very interesting. The challenge I'm putting to people and to myself and my collaborators is, let us make this absolutely the simplest possible way we can to explain all the variety that we find in the universe, everything that we find around us and things like that. And in the end, remember, this is a point that the famous John Bell made, who made those amazing discoveries in quantum mechanics. All the information that comes out of these experiments that are done at CERN is actually images or information. Well, it's a printout. The information is actually always, it's a little bit like what you see on the page 3. You see black dots on white paper, and then you see some words underneath saying what they mean. Mm-hmm. So everything that we know about the universe is deduced from variety, to which we attach meaning because of the structure that it has. So it's, I think it would be a very, very, this is my main project now with my main collaborators, is just to see how far we can go in explaining everything we know about the universe in the utterly simplest possible terms. So first of all, ratios are essential. So I allow the different particles to have different ratios of their masses. I allow the electromagnetic force or the electric charges to be much stronger than the gravitational mass, the strength there. So the electrostatics can be much, much stronger than gravity. And then the other thing are the ratios of separation. So if you have a triangle, one of the sides can be shorter than the other two. So that's a ratio there. And in fact, I would say that's the way to think about the expansion of the universe. If the equilateral triangle, if the sides of the triangle are aware of themselves, or shall we say the triangle is aware of itself, like we have this effect of proprioception. This is this sense where, as I speak, I know how far apart my two knees are, and I can bring them together, and I'm confident that they will bump when I do. That's a pretty amazing property. Now, if the universe is like that, the shortest side is a triangle would start off and say, all my sides are equal. But then after a bit, it would say, side A is shorter than the other two. And side A will say, the universe is getting bigger because the other particle is going away from the two of us that make side A. So that's how I think one should think of the expansion of the universe. That's not the way people think about it in cosmology. They talk about space expanding. So I'm not saying this is going to be right, that we're all going to get Nobel Prizes in a few years or anything like that. But what I'm saying is it's a very, very good exercise that should be done to see if we can root out all of the assumptions that don't really need to be made. And I think that consciousness has put a lot of wrong ideas into our head. And the first one is closely related to one that I already spoke about before, which is motion. When I do that, you see my hand moving. Now, that's clearly an effect of consciousness. That you can see me is clearly also consciousness, but that you see me moving. Now, is the movement as important as the instantaneous position of my finger? But the position of my finger, the instantaneous position of my finger, must be more fundamental than its being in different positions, because you couldn't say that it's in a move to a different position without those knowledge about the position. So if you look through the whole history of dynamics from Newton's great advance in 1687 all the way through, theoreticians have put position on the same status as they've given motion the same status as position, or rather momentum. So momentum and position have the same status. And that was formalized in very beautiful mathematical theory by the great Irish theoretician Hamilton in the 1830s. There were what they call canonical coordinates. Position and momentum are canonical coordinates. And that goes right through. That was the basis of the quantum mechanics that was then discovered by Heisenberg and by Schrödinger. And you see it exactly in Heisenberg's famous uncertainty principle, where the position and the momentum are said to be equally important. You can't measure both of them accurately at the same time. There's always some uncertainty around it. But the underlying statement, and it's right at the heart of the whole of quantum mechanics, is that they are on an equal footing. But I think that's very, very suspicious, particularly if really the reality, so what, in my book, The End of Time, years ago, I suggested that when we see a kingfisher in flight, incredibly beautiful, what is really in our brain when we think we see the kingfisher in flight is, shall we say, 6 or 7 snapshots arranged encoded in our neurons. They're all there in one instant, and then consciousness and the brain plays the movie for us. It's really a static arrangement of 6 or 7 snapshots, which we then experience as motion.
Let me see if I can get this straight. So when movies first came out and they were something like 10 frames a second or so, something small, maybe even 5 frames a second, they were shown on some wheel and there was someone dancing or a horse moving. And then they would say, look, the illusion of motion is being created because actually these are just different snapshots and you move them quick and your brain creates motion. You're saying, actually, that's what the world is. It's not just this film that produces the illusion of motion. The world produces the illusion of motion in concert with your consciousness or your perception.
Yes, I would say it's the if you say there are particles in my brain and there are particles in your brain and particles in my laptop screen and things like that, that's all interconnected. There are distances between all of these particles, and I would say in my brain at this moment, there's a whole lot of encoded images of you and myself, because I can see myself as I talk to you. And it's just that the brain and consciousness are playing the movie, are making it appear continuous. So the first task is but it's a huge task, but it's a very clearly defined task, is to say everything must be expressed in terms of separations between points, and every experience we have must somehow be correlated, explained by the differences in the separation between points. So in my image with the kingfisher, the images of the kingfisher against the background, there are differences. So I've got my 6 or 7 snapshots of the kingfisher, but first of all, the kingfisher's wings are in slightly different relative positions to each other, and also relative to the bank of the river against which it is flying along. So those are differences there. So that's enough fact from which my experience of motion can be explained or correlated. Now, a relatively easy one is the experience of heat. So we touch something and it's hot. But when the old thermometers, the mercury thermometers, was a bit of mercury in a tube, how did that get the temperature measured? Well, the atoms of the, or whatever the molecule, the form that the different particles in the mercury take, they are moved slightly further apart. So it's not. So if these ideas are right, it's not that there is any real motion at all. It's just that the greater separation between the particles, when I touch it, I feel that as heat. So the separations of the molecules in my finger when I touch the slightly hotter thing, that's then comes to me as the feeling that it's hotter, that body is hotter than my finger. And it's not to do with, so the standard story of a hot body is it's hot because there's lots of the particles are all moving around relative to each other at a terrific high speed.
Right.
So this is saying, no, there could be a completely different explanation. This is my principle: reduce everything to the absolute minimum that you can do it. And I believe that just the relative positions, all expressed as ratios of points, are sufficient to explain everything that we experience.
Let's linger on this for a moment. Can you explain, so the traditional account of what temperature/heat is, and then what it would be in your model, plus how that connects to entropy. Because as we were speaking about off air, you were suggesting that entropy was some emergent property or emergent illusion or not fundamental.
Yes. So the since people were already suspecting it in soon after Newton's time, but by the mid-19th century, people were suspecting that there really were atoms, and that when we feel heat or hot bodies, they really are just atoms or molecules moving relative to each other. And the faster they move, the hotter the object is. And then so then there was very brilliant work done from 1850 through to 1875 it started with somebody called Rudolf Claudius. He was the person who first formulated the second law of thermodynamics, that very, very simple, that heat flows spontaneously from a hotter to a colder body, but never in the opposite direction. And very soon after that, he started developing this atomistic explanation of the laws of thermodynamics, which were that it's just a measure of how the particles are moving around that creates the impression of heat. And then Maxwell, the great Maxwell, who developed the theory of electromagnetism, he came in and he then found the expression for how the velocities change. So Clausius had originally just assumed that they all have the same velocity, but Maxwell saw, no, that can't be right. Some must be moving faster than others. And then he proposed an expression which is called the Maxwellian thermal distribution, the expression for that. And then the numbers that have the different velocities, the different speeds, that's then associated with what then became called the entropy. So entropy is a measure of how things are spread out and how they're distributed. So the easiest way to think about entropy is actually not where there's motion, where you've just got checkers on a checkerboard. So 8 by 8 squares, and you've got a whole lot of checkers. So you've got 1,000 checkers. So you could put all the checkers on one square. There's only 64 ways of putting all the checkers on one square. There's 64 squares. So there's 64 ways of doing that. But then the great insight that led to the definition of entropy was by Boltzmann, who said there are vastly more ways of distributing the checkers by spreading them out uniformly on all the squares. So, you get a huge increase more. And then how entropy is defined is you then actually take the logarithm of that number of ways that you could distribute them. So the entropy will be minimal if you put all the checkers on one square, and then it will go up to its maximum possible value if you distribute them in the most uniform way that you possibly can. And then this leads to the idea that entropy defines the direction of time, because if you had particles in a box, and they all start off in one corner, that they're all moving relative to each other, but they're all in one corner. So that means they've got a low entropy because they're not uniformly distributed. And after a bit, they'll bump around and bump into each other. And then they'll spread out. And after a while, they'll fill the whole box uniformly. So that was how the increase of entropy was explained. And then I can't remember I think it was Ludwig Boltzmann who first suggested that we get our notion of the direction of time from the increase of entropy. So that was how the idea that entropy was very significant. And it then turned out that a huge number of things could be understood with this concept of entropy. But what is very significant, and what then got totally forgotten was this final state where everything is uniformly distributed relies upon the box. If the box wasn't there, what would happen? Now, the reason this is all, I would say, intellectual inertia. So the laws of thermodynamics were discovered all through an absolutely wonderful book that was published in 1824 by the Frenchman Sadi Carnot. And Carnot was interested in what's the maximum efficiency that a steam engine can have. And he didn't quite get it right, but he got very close to it. But one thing that he did, so the key thing, first of all, if a steam engine is going to run continuously, first of all, you heat up the steam from the furnace and you expand the cylinder, and that does some work, moves the steam engine forward. But then you've got to get it back again for continuous operation. And to get it back again, there's still some heat in there, and you would have to exert some work. So you've got to cool down that steam to get it back to the starting position. And that wastes some of the energy. So this was the second, that's one of the formulations of the second law of thermodynamics. Some of the energy, some of the heat is lost for continuous operation. So that was a great insight already of Sadi Carnot, and then that was then formalized in later on. But all of that still only works in a box. So then when you look at all these wonderful papers by Clausius, then by Maxwell, then by Boltzmann, and later on by the American Gibbs, they're all using systems in a box. And what is interesting is there's just one of them who really pointed out that his whole theory based on probability, the probability of these distributions, he said this will fail if the system I'm talking about can expand into infinite space, unlimited space. He puts that as a caveat. He also says there must be a restriction on what the momenta can do. If the momenta can become infinite, my system won't work. But he doesn't explore what happens if that's not the case. And that's been virtually ignored. I think I haven't seen anybody draw attention to that as really very important before I did it myself about 10 years ago. Now, that just makes you think. When things are working very well, because, I mean, the value that came out of this notion of entropy, it's just amazing. I mean, the first quantum effects were discovered through the study of entropy. Endless results in all sorts of technical fields. Understanding communication, Shannon with the notion, Shannon entropy. It's just incredible. But all of them actually depend upon a system that is either in a box or it's bounded. Also, it's when there's a finite number of possibilities. For example, if you have a deck of cards with 52 in it, your chance of drawing the ace of spades is 1/52. But if there are infinitely many cards in a deck, your chance of getting a particular card is 0. This is essentially the simplest form of what Gibbs was saying. My whole system will fail. So this is just a good example of how science can go incredibly successfully for a long time without realizing what's going, the assumptions that are being made. Now, the great problem with entropy and the whole idea that it's what determines time, the direction of time, is that you have to have some initial state. So I talked about all those molecules being in one corner of the box. How do they get there? Now, this comes into what's called the past hypothesis. So this already goes back to a debate with Boltzmann in 1896. Was there a special initial? So the idea is if entropy is determining the direction of time, Well, first of all, one immediate problem is we couldn't be talking to each other if entropy hadn't already reached was. Entropy must be way below any possible maximum it could have. Otherwise, we couldn't talk to each other. It's obviously clear that the universe is not in maximal entropy, nowhere near. But if entropy is really is the fundamental quantity, then the only way that you can explain that you and I can still talk to each other is that the universe must have started in an incredibly low entropy state, which cannot be explained on the basis of the known laws of physics. This is what Richard Feynman said about, when was it, 50 years ago or something, certainly 40, 50 years ago. He said, to understand why we haven't got maximal entropy now, the only way to explain that is to add to the known laws the assumption that in the past there was a very special state of low entropy. And that's now been called the past hypothesis. And people struggle to find out what it was like. Well, my conjecture now is that is completely and utterly wrong. It's because entropy does not apply to the universe. It's just naive extrapolation from what is perfectly true in a box. Now, because all around us we can find ice, we can make ice in a refrigerator, we can put ice in a corner of a box, and it will melt and then evaporate, and then you will get what's called heat death. So already back in 1854, 4 years after the laws of thermodynamics were discovered, Helmholtz in Germany talked about the heat death of the universe. Everywhere, everything will be uniform, and there will be no life, heat death. This has been a horrendous sort of nightmare for the universe. But it could be just a complete fundamental mistake in thinking that what happens in a box is a true model of what happens in the whole universe. This is what my book, The Janus Point, is about, in a paper that, with my two collaborators, Tim Kozlowski and Flavio Mercati, we published 11 years ago. It was in Physical Review Letters.
When you mention that physics happens in a box, are you referring to a closed system?
Yes. Well, there's the danger with that word closed is, in dynamics, people mean by that there are no forces acting on the system in addition to the system you're thinking about. They're not meaning by that whether it's in a box or not. So a closed system normally just is the assumption that, say you've got 100 particles and they've got forces that act on each other, but there aren't other particles far away that are also exerting forces. So that word closed is a bit dangerous. I would prefer to say confined if I want to, rather than closed.
The reason I was asking about that is that there are studies in physics of open systems, and there have been for decades, no?
By open systems, what they mean is systems that interact with a thermal bath. So basically, so you can have say particles kept within a membrane, but there are particles outside in what's called a thermal bath, and so heat and energy can pass between the exterior, and that's what they mean by an open system. They don't mean, so I'm meaning something quite different when I'm in the Newtonian n-body problem. If you, in the simplest case of three particles, in Newtonian terms, those three particles, if the energy and the angular momentum are exactly zero, then what always happens in both directions of Newtonian time, you will always finish up with two particles going around each other, forming a clock, a rod, and a compass direction because of the way they behave. And the third particle is going away in the other direction. And that system, the Newtonian size, grows to infinity. And that's what I call that's not a confined system. That's the one where we found an alternative arrow of time, which is nothing whatever to do with the entropy or the system in the box. And it's precisely, if we go back to page 1, it's precisely that quantity on the expression on page 1 that I call the variety. So those are the A, B, and C. Those are the lengths of the sides of the triangle. And that quantity is scale invariant. But as the ratios of the sides change, that increases. That expression, just if it's just you've got 3 particles and their separations between the pairs are A, B, and C, that quantity will start off, in fact, I think it's 1 over the square root of 3 when you do the calculation. That's the minimum value it can have as an equilateral triangle. And then as it gets more and more pointed, that quantity will increase, not steadily, but with fluctuations, but it will go on increasing upwards. And that defines an arrow of time. And I think that is much more likely to be what is really determining the direction of time in the universe as a whole than anything to do with entropy. And it's based on ratios. And this is, it was recognized. The Physical Review letters, they sent it to 5 referees because we were saying, here we've got a major new thing. So they wanted to be sure they got it right. And they then decided on the basis of what the referees said, they gave it an acorn. It's a sort of recognition as a special paper. And then they also got quite a distinguished person in quantum gravity to write comment on it. So, it was recognized as being definitely interesting.
Are these A, B, and C's and D's and so on, are they allowed to be any real number?
Any real number greater than 0.
So you have continuity in that you have a real line?
Yes, so what I have, so in my minimal ontology, the minimum sort of assumptions I make about the universe is that there are points, and you can say they're particles but they have 0 size. Very important in this is the particles have 0 size. That enables you to define scale invariance very precisely. And then those ratios of the separations can change, and it can go from the most uniform distribution that it can have. It's always a positive definite quantity. So it's positive and it's always greater than 0. And the absolute minimum is very, very uniform, but except for 3 or 4 particles where it's the equilateral triangle or the regular tetrahedron, in nearly all cases, it's not exactly uniform, and you can see that it's in page 3. That's really what it's really like at its absolute minimum for 5,000 particles. The one on it's an incredibly spherical ball, and on the right it's an equatorial section through. But you see, it's uniform, but not exactly uniform, and that's why structure forms totally naturally in the Newtonian theory, in the Newtonian Big Bang, but they have such struggles with it in cosmology because it's based on everything in general relativity is based on averaging things out and having continuous distributions of not of separations between particles, but continuous distributions of fields, and that's where all the problem comes from in general relativity.
Is there a reason that you say that the size is 0 instead of saying that the size is ill-defined or not unique?
Well, the size is if you imagine that there's a ruler outside the universe, then you can say the size is 0. That's where on page 1, that's where the quantity under the square root can become 0. But really, if you say, so I joke that to my children, I say, when I'm buried, on my gravestone, it should be inscribed, nothing but ratios. It's amazing how that is forgotten. Let me point out, it's forgotten by Einstein in his general theory of relativity, because the key quantities that define his theory are proper time and proper distance. They are not ratios. So his theory does not rest on secure foundations. I'm not saying that but it needs certainly sorting out. The foundations of general relativity need to be properly clarified. And in fact, my collaborator Tim Kozlowski has gone a long way, I think, in really putting general relativity in the shape it should be on much more secure foundations. They don't rest on this imaginary rule of an imaginary clock outside the universe.
Okay, let's talk about Newton. We'll get to Einstein. In our last conversation, I recall you said something about how Newton's gravity was inherently driving the universe towards states of increasing structural complexity and order. And you measured this with that scale invariant complexity, which I believe now is called variety.
That's what that's because I'm now coming back to my think that's the most well, first of all, we were calling it complexity for a long time, but the problem with complexity, everybody uses that word in many different senses, and quite often it's not well defined. We at least had a very well defined notion of complexity, but now I'm now calling it variety. In a tribute to Leibniz, because it was through Leibniz that I was thinking about. I mean, once I read Leibniz back in 1977, I was looking out for a quantity to characterize variety, and then it was in 2011 I realized that it was actually the Newton gravitational potential made scale invariant, and this is actually so that second quantity on page 1 in the round brackets. If you change the sign of that's the Newton gravitational potential made scale invariant by the quantity which measures its size.
Now, how would you accommodate gauge fields relationally?
Well, they have internal degrees of freedom, but in fact, actually, in a way, I would say the first, what ought to have been discovered as the first gauge field is actually what my Italian collaborator Bruno Bertotti and I did in 1982 in our paper there. That isn't a non-abelian gauge theory. The simplest non-abelian gauge theory is the three-body problem. That's because in rotations, when you have rotations, they do not commute. If you have one rotation A and another rotation B, the effect of B doing A first and then B is not the same as doing B first and then A.
Uh-huh.
You get a different result. So that's an example of non-commutativity. Non-commutativity is right at the heart of quantum mechanics as it's formulated at the moment. So what Bertotti and I showed in 1982 is that that the Newtonian n-body problem for arbitrary number of particles, 3 or more, if the if the angular momentum is exactly 0, that is technically a non-abelian gauge theory.
Well, wait. Just because you have something that doesn't commute, what makes it a non-abelian gauge theory? It just makes it non-abelian.
Because what really, now you're getting into something that I call best matching, which is what really is underlying gauge theory. So if I have two, I don't think I've got my trials now with which I illustrate.
The trusty diorama.
But if I have to, I'll have to do it. Just imagine that my two hands are two triangles that are not the same size and not exactly the same shape. But I put one on top of the other until I rotate them around until I get the difference to be absolutely minimum. But I also divide by quantity so that I'm only talking about the shape. So that's what I call best matching. So if I don't worry about the overall size but just the shape. So if if I leave the size as they are, so I've got two triangles that are more or less the same size, but they're not exactly the same. So I put one on top of the other, and I give each vertex the name 1, 2, or 3. I number them 1, 2, or 3. Then, as I put them I put them in any position, and then I will find that particle 1 has moved a certain distance. So I take the mass of particle 1, and the distance is I've squared that distance and multiply it by its mass. I do the same for particle 2 and the same for particle 3. So then I've got a quantity which measures how they have not been brought to perfect overlap, or the closest overlap you can get. But as I rotate one relative to the other, that quantity is positive. There must come just one precise position where that quantity is minimized. And that quantity, I say, in that situation, I say the two triangles are best matched, and the quantity is the best matched thing. And that is actually what is going on in all of gauge theory, in more complicated situations than just with triangles. And that, by the way, is also what underlies what's going on in general relativity, but in a much more sophisticated form. It's really just best matching. As you go to the limit where the distance, it's all expressed with what are called what are they called? Lie derivatives and things like that. But in its absolutely simplest form, it is what I call best matching. And that concept of best matching is, now you can find it cited every now and then in the literature. People are recognizing that is what's going on. And it's again something that you can visualize very, very easily. So that's actually what is underlying gauge theory. And the simplest example is with a triangle with 3 particles. And in that case, you get 3 particles whose angular momentum is exactly 0. So that's the condition that comes out of a gauge, of a non-abelian gauge. It's the simplest non-abelian gauge theory. But all of the gauge theory is just that writ much larger. And so is general relativity in some of its key aspects.
So I want to get to this whole quantum without quantum, because when people say something without something, like John Vervaeke is a philosopher, he says he wants a religion without religion. I always wonder, like, what are you referring to? Because if my wife asked me to clean up, I could say, yeah, no, I'm doing the dishes without doing the dishes. So to justify that usage, what is quantum without quantum? What's being saved? And what is the first quantum referring to that's different than the second quantum?
What I'm suggesting is that all the evidence on which quantum mechanics is based can in principle be explained in a completely different way without any wave function and without any Planck's constant. That is if you like, the outrageous claim I'm making. So what I certainly can do, I think I can make a pretty plausible case that there could be a completely different explanation than going on. So let's go back to the evidence on which quantum mechanics was based, and what the founding fathers were trying to do from about 1925 through to about 1933, when the result was there. So what they were trying to do, it was a huge role, was explain the structure of photographs taken in the laboratory. They were photographs of cloud chambers. So it's a wonderful story of how the cloud chamber was invented by Wilson, was the man who did it. And then he was trying to make clouds, things like clouds. And that's what it's a cloud chamber. And suddenly he saw these curved tracks. Suddenly he saw these tracks in this thing when he it was in a metastable state, and he did the thing which made it then form all these vapor bubbles. And suddenly in the vapor bubbles he saw all these tracks. that was the discovery of cosmic rays. But then the great mystery that they were trying to understand when they were talking about the foundations of quantum mechanics was to explain the structure of photographs taken in a laboratory. And in fact, all of the evidence for quantum mechanics. So I once did some practical work in astrophysics, which was to measure the effect, the spectral lines in the spectrum of a variable star. And what I was looking at through a microscope was it was a photographic emulsion what I was looking at, and as I went along, it was where there was a double, where there were two spectral lines close to each other, a doublet. And as you went along, it just got darker and darker. And then there was a place where it was darkest. That was the center of the spectral line. Then it went down again, and then it got darker again. So that was a photograph. I was measuring the darkness in a photograph. That then was expressed in terms. That was the raw data. I call that the raw data, the evidence in the photographs. But then that was then processed data became interpreted in terms of frequencies and wavelengths. But think about Newton, for example, when Newton saw the colors of the spectrum on the wooden paneling in his room in Cambridge, the structure of the molecules in his retina were correlated with very subtle changes in the chemical composition on the surface of the wood. That's what was there. It was over a century before those. That was then formalized as wavelengths and frequencies. So quantum mechanics in that form was based not on raw data, but on processed data. And as I like to say, processed food is not good for us. So I think processed data is bad for theorizing. So there is a completely different explanation possible for those cloud chamber photographs that Wilson obtained.
Okay.
Suppose that at the instant at which that happens, some deity could take a snapshot of the whole universe. And that universe satisfies just one condition. That quantity that I call the variety has a particular value. So suppose we have a universe with 1 trillion particles in it. Now there's a huge number of shapes that will all have the same value of the variety, that can all have the same value of the variety. So there. So the deity takes snapshots of all of them. And then he looks carefully through all of them. And then in one of them, he finds in a tiny part of it is exactly the laboratory where the photograph is taken and the photograph itself. It's sitting there. And the explanation is just determined by the statistics. We'll come on to this. There are probabilities of shapes. And the explanation for why that photograph and the laboratory is in part of just one of those shapes is statistical, and the fact that the variety has a particular value. That is an explanation in principle. Now, this brings in the difference between holism and reductionism. The whole of physics, certainly since Newton, but before that, has been reductionist. All of variety has been washed away. Newton got rid of all the variety in his absolute space. And so what was left for these it's very interesting to read the 1927 Solvay conference when all the great founders of quantum mechanics got together and discussed its foundations. They were all thinking in very reductionist terms. The furthest they would think about things would be what could happen in a laboratory. They weren't thinking about what the effect of the whole universe might have. But that's very critical. What the effect of the whole universe could be.
Dirac had his large number hypothesis.
Yes, but he didn't manage to go anywhere with it. But in fact, this is the sort of thing that is coming out of these ideas that we're developing. So let's just look at the. Let's look on page 1 on that extraordinary rich filamentary structure there on the right.
Mm-hmm. What are we looking at exactly? What was it that created these images?
That is just one. It's a distribution of the particles that has a value of the variety, which is what is said to be critical. It's either a local minimum or a saddle. So the value of it's a value of the variety, which if you change any of the particle separations by just a small amount, the variety doesn't change. That's a critical value. And that's the condition that has generated that thing.
Okay, let me see if I got this correct. So if we were to pick a variety number, remember the equation that is above, let's say we picked variety 110. So there are a variety of different ABCs that you can put in there to get you the number 110. Now, if you look at these different numbers, maybe there's, I don't know how many of them, 1 trillion different numbers that can get you 110 depending on the amount of particles. If you look at it from a God's eye point of view and you take all the snapshots of what can be 110, and then you say, okay, if I was to vary this, would that change my variety by much? Oh, this changes my variety a great deal. Let me go to the next one. And you keep doing that until you get to one that changes the variety the least. You're looking at that right here?
Yes, that's got to be the complete. It's not just one part. If in that one with all those filaments on the right on page 1, if you move any of the particles by a small amount, you won't change the variety. It will stay essentially exactly the same. All of them can be changed by any one of them can be changed by a small amount without changing the variety. That's what has generated that particular structure. And by the way, there's a huge number like that. It's you know what factorial means.
Yeah.
So essentially, the number of ones like that is 1,000 times 999 times 900, all the way down to 1. It's just an incredible number of them. It's incredibly creative, this quantitative variety. But why don't we briefly turn over the page because it's quite striking. So on page 2, let's go to page 2.
Before we move on to page 2, what was the point of showing this? Like, what were you trying to convey on page 1?
Oh yes, no, that's it. Yes, because there's a marvelous statistical. Do you see? If you could look at it with a bit of a magnifying glass, but you can see it with the eye already. All the smallest separations are almost identical. You won't find anywhere where two particles are really very much closer to each other than the others. And that's exactly that's because if you go up and look at the expression for the variety, it's 1 over A plus 1 over B plus 1 over C. So if any of those A, B, or C goes to 0, then 1 over that quantity goes to infinity. So, and if you're fixing the value of the complexity, that's you can't do that because you'll overshoot. So the explanation. So you will find it's incredible. All of those smallest separations are incredibly nearly equal, the smallest ones, and that is a holistic explanation And by the way, it does exactly what the Pauli exclusion principle does in quantum mechanics. The reason a friend of mine, Harvey Brown, makes this very, very clear. If it wasn't according to quantum mechanics, if it wasn't for the Pauli exclusion principle, if I just put my two hands together like that, there should be the effect of a hydrogen bomb going off, but it doesn't. And that's because you can't, in terms of position, you can't get two particles getting close to each other. It stops them doing that. But this is one of the reasons why I conjecture that there is no quantum at all, because it's all just saying, if I specify just one value of the variety, and I've got to go through all values of, if I'm going to start from the lowest value and let the variety go on up, creating ever more different structures, and we'll look at that in a moment, I've got to fix each. So I call that the age of the shape. So the age is 0 when it is at absolute minimum, and the age is slightly greater when it's above the minimum. So the difference between the variety at the value you've got and the absolute minimum you have, we call that the age of the shape. That's my collaborator Tim Kozlowski and I. And that's really, if you think about it, how do you recognize how old things are? Well, I mean, just looking at you and me, it's blindingly obvious I'm older than you. And so this is, but everywhere we look, we see, with a glance, we can say some things are older than others. There's a walnut tree out in front of the window where I'm looking at. Well, if there was a small walnut tree next to it, it'd be obvious which is the older one. And it's everywhere we look, we see, but also in stars. Stars are clearly, some stars are much younger than others, and those are the ones where they've only got hydrogen and helium in. But as they get older, there's more helium relative to hydrogen, and then other nuclei come in as well. So everywhere in the universe, we can see, first of all, the universe gets older, and that's measured by its variety. And then within it, there's lots of substructures which also have their own relative ages relative to the whole of the universe. So this is a quite different, concrete way of thinking about the universe and getting rid of time and replacing it by age. I'm going to quote Shakespeare now, because I wrote an essay called The Nature of Time. And in it, I said that Shakespeare did not attempt to say what time is, but what the effect of time is. And I quote the start of his second sonnet: "When 40 winters shall besiege thy brow, and dig deep trenches in thy beauty's field."
Mm-hmm.
So the effect of time is to make the wrinkles in my face. That's the effect of time. That's the measure of age. And we should think of so reductionism. So Newton has not got an awful lot to answer for. Newton said time flows equably without relation to anything external. Well, I mean, he's just washed away all variety. But the evidence for time is in structure.
Would this be a prediction against the heat death of the universe?
Oh, absolutely, yes. No, but if I'm right, it'll just go on getting more varied forever, ever richer structure, and it has been doing that up to now.
How do you do that without contradicting the second law?
That the second law applies to systems in a box. If the universe is not in a box, all bets are off.
Now, if the universe is open, what is it open to?
Well, first of all, if you remember what I said, it's got to be on my gravestone: nothing but ratios. If it's 3 particles, if it's a universe of 3 particles, all it means is that one of the separations can get infinitesimally small compared with the So you've got two particles here and one out there. And all getting larger just means that the ratio of when you divide the two long separations by the short one, that just goes to infinity. That's what an open universe is. That is a universe that can go expand forever. But it's a ratio, nothing but ratios.
Okay, so would you say the ratios are what are fundamental, or the particles that create the ratios? It seems to me like the ratios are defined in terms of the particles.
Well, yeah, I would say you need both. You need both. I mean, well, you've got to have the particles, and then what counts is the ratios of the separations between them.
My understanding is that you're using this to get certain features of physics like the Born density or spin or fermions and Pauli exclusion, as you mentioned. It seems like a toy universe that you're just toying with. Are you suggesting that this is what the universe is fundamentally?
If I'm right, that is what it is fundamentally.
In other words, it sounds like you're saying there is no box, there are no fields, maybe, there is no absolute space, there is no so and so, there is none of this. There must be a yes somewhere, like some ontological fundamental quantity or object. So, what is fundamental in your theory? Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org. What is fundamental in your theory?
I cannot do my theory without assuming. I think they could just even be mathematical points. You didn't call them particles. They're points because they have zero size, but there are non-vanishing distances between them. But it's not the distances. The distances are, so to speak, there to enable you then to form ratios of distances. The things that are really real, ontological, are the ratios of the distances between points. That's my absolute minimum that I can do. And I'm certain I can already build an extraordinarily interesting universe with just that and nothing else. But to really get all the effects of the different types of forces, I will need a more generalized form of the variety, that one that is so simple there. That's the simplest one you can possibly, but it's extraordinary how much already comes out of that. It's just, people just don't know about it.
What about the number of points?
Well, I've now got a way of doing that with infinitely many points. So an infinite Euclidean space with infinitely many points in, and there are different ages of that universe. At its age 0, if you take any large region containing, say, 1 trillion particles, the distribution will be very, very uniform. A little bit later, when the age is a bit greater and you take a large number, it'll look like the one on the right. But I tell you what, let's just briefly go on to page 2, Curt, because it's very interesting to see the effect of this. A colleague of mine, Hemant Shukla, did this for me.
Sure.
This is 12 of these shapes of 100 particles each, arranged in order of age. Age 0 is top left, as you see, very uniform. And then the variety between the one top left and the next one along, I've said that's the unit of age.
Uh-huh.
And then they're ordered in age. And look how structure forms. Very uniform. Here you see, this is why I think we may have stumbled on the nature of creation. Just look as that structure increases as you go from age 0 through to 4.6 bottom right. So you start getting these filaments, and you notice the filaments all have the smallest separations pretty much the same. Then at age 1.1, you've suddenly got something which looks like a pair of scissors. Two
Yes.
circles have appeared.
Good eye.
And then look particularly, one that I really particularly like is age 3.2, bottom left. There's two perfect filaments and then a near perfect circle. And this is in 2 dimensions. That's why the separations get slightly larger as you go out to the edges. That wouldn't happen in 3 dimensions. You have filaments in 3 dimensions. By the way, there is she's working on it now with a supercomputer in Lisbon, Maria Lorenzo, who's started working on these ideas. She's doing a master's, and she's already found 1,000 particles in 3 dimensions with lots of filaments, and she's starting to analyze them now. So something very interesting might come out of that. That's in 3 dimensions.
These are some delightful photos or mock-ups or what have you. What is it supposed to be? Are you supposed to be showing this is galactic formation? This is how life emerges. This is what's going on in your brain. Like what are we supposed to infer from this?
Well, I would say it's paradigmatic of all of those. I would say what is the most fundamental aspect of our existence? It's the huge range of shapes of things that we see around us. If you go back to the ancient atomists, I got halfway through it. It's a long poem by Lucretius on the nature of things, De Rerum Naturae, 150 BC or something. I think he wrote it around then. And you see, what he was really interested in was the explanation of the shapes of things. And he talks, and to explain that you have all these remarkable shapes. I mean, children look like their parents. All oak trees have the same sort of structure and things like that. And to explain that, he introduces atoms. He calls them primordial seeds, which have shapes and different sizes. And each macroscopic thing he wants to explain, he invokes a new primordial seed with the appropriate shape and size to explain it. But this just shows early on what really fascinated people was the different shapes you see around us. So if you think about it, that is actually the most fundamental feature of our experience, the huge variety of shapes. I mean, if people are watching this and can see both of us at once when it's shown, they'll just see that you look pretty different from me. You've still got a good head of hair and so forth. But I mean, just look going around at the different amount of structure that there is. That is what should be explained. But what we've stumbled on is a holistic way of explaining shapes, and you see it, and it's all done with this one quantity. The simplest form of variety already does extraordinarily well. As you see it going through, there's 12 ages, not 12 ages of man, but 12 possible shapes of a 100-particle universe in 2 dimensions. But already there, it's pretty interesting. Look at it. And each one of those, at each age, there's vast numbers that have the same sort of age, but very different structure.
Now, what would you say to someone who says, if this is the case, that we're just increasing in variety and life is evidence of this variety, or life should emerge, then why is life only on Earth? Why don't we observe much more of an abundance of life? Wouldn't this predict that life should be far more abundant than observed?
I think this could be, I don't think Maria in Lisbon is going to be able to do the numerical calculations that would show this, but what one can anticipate at the moment, the only calculations that have so far been done show what the variety is like very close to its absolute minimum. I would think that if the variety gets much larger, what will happen? Well, it's intuitively clear it will. You will form lots of clumps. Lots of clumps of things. And it will be like the first stars forming. And we know that within the stars there are hydrogen and helium nuclei. These are pretty well the simplest structures you can have. So I would think that when the variety is really got a large value, what you will find typically is things that look like stars, and then the stars will gather together in what look like galaxies. And within the stars, you will just have very simple structures. So what are molecules? If you just think about, do you remember these sort of dumbbell images you have of molecules with sort of connecting things like that? Those are basically relatively simple shapes. Each of those considered by themselves will have a low value of their variety. So a star will basically is nuclei of various structural complexities. So there won't be any really individual rich structures within a star. It'll just be full of lots of things that look much the same and quite interesting structured. Now, the only place where in the solar system where we know there is interesting life is on the surface of the Earth, and it's I think you could show that these ideas will predict that very special complex structures will only emerge in very special places. I mean, within the solar system, there's a lot of speculation that there could be life of some form in the satellites of Saturn and Jupiter, in the liquid in their seas. Whether they would be talking to each other like you and me is another matter. I mean, one rather doubts that. But there seems to be, I mean, I think the widespread view is that very basic forms of matter are of life are likely to form. That I mean, after all, we know on the Earth that very simple unicellular life developed extremely soon, but then it was a long, long time before it became multicellular and really interesting structures appeared. So my guess is that it will be a statistical question and depend upon the value of the variety, the age defined by something analogous to what I call the variety. That's where, but there will be sophisticated structures appearing. I mean, if we go back to page 1, you can just see how extraordinary the structures are there.
Mm-hmm. Now, suppose you had a one-electron universe. Do you imagine that there would be multiple points that comprise that universe? Or would it just exist?
Well, first of all, I would... first of all, you've got to have 3 particles have an interesting shape.
Oh, no, what I meant to say is the electron, if you want to think of the electron as the wave function of the electron, like some people conflate the electron with its wave function.
Yeah.
But it doesn't matter. The point is that you have an electron, what we think of as a point particle. Does that correspond to a point particle in your picture? Or would an electron itself comprise 1,000 different points, like it would correspond to n equals 1,000 here?
Oh, no. I would certainly think of the electron as being just one point.
Okay, so then what gives rise to the probabilities, like the Born density, if you don't have a wave function here?
Right. Well, let's go on over to let's now turn to page 4. This is where there are probabilities and Born densities without there being.
Interesting.
So you see, this is called the shape sphere. This concept appeared in about 30 years ago, it was formalized in Newton's theory of gravity for when there are three particles. The shape of a triangle is defined by two numbers. Two internal angles define the shape of a triangle. So we've got this image here. So because the surface of a sphere is two-dimensional and two numbers define the shape of a triangle, you can represent all possible shapes of triangles by points on the surface of a sphere. So that's shown here. So the shapes that are mirror images are at the same longitude but opposite latitudes. So there's two equilateral triangles, one at the top and one at the bottom, the North Pole and the South Pole.
Mm-hmm.
Then there are the degenerate triangles, which are really just on a line. That's three particles on a line, and that's the equator. And there are 6 special points there where they're all in a line, and one particle is bang in the middle between the other two. But then there are situations where two particles are very close to each other and one is on the right. So that's where I think you're seeing it in color, aren't you? There.
Yep.
That's where two particles are very close to each other compared with the distance to each other. And as they get very close to each other, that's where the variety becomes infinite, goes up to an infinitely high peak. And then the contours, the white lines, are contour values of the variety. So the variety has its absolute minimum at the equilateral triangle, and then it increases and it grows all the way up to infinity, where two particles are, that's where it gets deep red, and the two particles are very close, much closer to each other than the distance to the third. And then there are 3 saddles where the value, it's like when you go through a mountain pass. Well, you can see that its image, the image is in the contour lines that I've shown there.
Mm-hmm.
Now, the key thing about this, I was talking about best matching before, that best matching defines a distance, a uniquely defined distance between shapes. It just relies upon points in Euclidean space. So there is a well-defined distance on the surface of that sphere. So the surface of the sphere, it's a pure number. It has the area 4 pi. Now suppose you have a tiny little patch there on that sphere, which corresponds to possible shapes of the triangles, which are, it's a set of triangles which have nearly the same shape, but they can be represented as a little patch of a certain area. So let that little patch have the area A. So then the probability, it's a probability measure or an existence measure, if you like. So you divide A by 4 pi, and that tells you the probability that you will have shapes that satisfy the condition that they lie in that point. And then very interestingly, as you go along one of those contours, you can have the same condition. You can say, I'm going to fix the value of the variety, and then I'm going to say, I'm going to mark out the stretches along that contour where no angle is greater than 90 degrees. And then I've got the probability of finding, what's the probability of finding triangles that have less than, all their angles are less than 90 degrees. And that's mathematically uniquely defined, just comes straight out of Euclidean geometry. And if you say that the contour lines define time or age, I would prefer to call it age, that's analogous to the time in quantum mechanics. It plays the role of time in quantum mechanics. And then you've got probabilities for the shapes at that given time. And that is like a Born density. So there is a Born density existing. Shapes have a Born density without any wave function and without any Planck's constant.
Okay, so I see how shapes can have a probability associated with them, but to call them a Born density, you would have to show some correspondence between that and the Born density. So have you been able to calculate that?
Well, not if I don't need to do it, because the only evidence that supports quantum mechanics is the outcome of experiments. You never, I mean, if you read Heisenberg on interpreting quantum mechanics, he says we can never know what the wave function is doing or the particles that are being governed by the wave function. All we can see is the outcome of a
Right.
measurement.
Yeah.
If we can reproduce all the results of the measurements in
Okay.
this way, that's all we need. So all the evidence for quantum mechanics is in the Born density, the hard evidence. I mean, you read John. There's the really wonderful paper by John Bell called "Quantum Mechanics for Cosmologists," and he just makes the point that the evidence. I think he uses the expression. You could say the evidence for quantum mechanics is in a printout on paper.
All right, let's go to the last page. What are we looking at here?
Well, this is a very interesting thing. So this is what I'm hoping the sort of study. So this is intriguing structure that comes. This is very typical. This was made for me by Manuel Izquierdo, who was that Spanish student who found the amazing filamentary structure that we were just looking at. And what it turns out, you get these filaments, and the filaments, because it's in 2 dimensions, the separations get larger as you get to the edge of the disk overall. You can see that clearly. But what comes every time is that there's a hierarchy. So in the middle, there's I'm seeing it in black and white, but I think it's in red, isn't it?
That's right.
The long filament, the separations are the shortest ones there. And then you'll see in different colors. I got Manuel to color them according to the length of the separations. And you see there's a hierarchy. That comes in every single one that you generate. There's a hierarchy of separations. Well, that sort of smells a little bit of quantum mechanics. All I can say is it's not understood. There's as of now, I mean, the experts in Newtonian gravity, and I think I can say I know the top 5 or 6 quite well. They were very struck with that discovery that the Spanish Manuel made, and there's no understanding as yet exactly why these particular structures are forming, but it's very remarkable that they do form. This is a major discovery in Newton's theory of gravity, only 4 years old. I mean, centuries after Newton formulated his theory. And why do you get this hierarchy that's going up there? Well, I'm hoping that Maria in Lisbon and perhaps others can do further tests that will show what's the cause. Provide an explanation for it. But it is quite striking. So this again, you see, what should have happened would be to do. I would say this is where you could sort of talk about consciousness, that if I had asked Manuel to make the smallest separations with violet color, then next blue, and go through the spectrum where the shortest separations, which looks like shortest wavelengths, get violet and then blue and go all the way through to red. So then the ones that are scattered around would be red. Then I would say that consciousness is the great gift, in that it is highlighting the structure. So first of all, there is a structure in the universe. It's a mathematical. The universe has a mathematical structure. But if it was just points with all the same color, so to speak, just black dots on white paper, it wouldn't look nearly so interesting as this done with the colors there. So I think consciousness does 2 things. First of all, it's enabling us to well, it makes us aware of anything. Without consciousness, we would know nothing. But secondly, it's picking out the details in a very wonderful way. But it's also making life very exciting, because think about motion. We just recently had the most famous racehorse in the world, the Grand National, was run in this country a week or two ago. I mean, nothing is more exciting than the finish of a horse race. And everybody gets incredibly excited. But maybe it's really all just photographs, and then consciousness is making it appear to us as an incredibly exciting horse race, and giving us I use the expression a great gift, the great gift of consciousness, but at the same time deceiving us monumentally.
Mm-hmm.
So I think that the challenge is to see how we can explain everything with the absolute minimal ontology. And I don't think we can go less than points in Euclidean space, but I think virtually everything can be done with ratios of things in Euclidean space. You can have things that are analogous to ratios of charges. I mean, we know that there are color charges and so forth. So I think all of this could be built into. I mean, if these ideas catch on and people get going, lots of people will be exploring with supercomputers what can be done. Because the calculations, I mean, a colleague of mine pointed out, I said, well, maybe the shapes of molecules will just come out. Here I'm sticking my neck out. I mean, I've said this to distinguished physicists, and they've just shaken their head in despair at Julian. He's crazy. He's a nice chap, but he's crazy. I mean, quantum mechanics just cannot be used to calculate the shapes of carbon molecules. Anything that's a bit complicated. I mean, it's all sorts of tricks have to be used to say what the shapes are going to be. But the calculations that generate these shapes are really very simple by comparison. I mean, they're not different. They're not differential. They're not really. They're very simple equations.
Okay, so let me see if I have a handle on this. So you
Yeah.
have violet, you have indigo, you have blue, green, yellow, orange, red. Okay, let's look at this image. So the way that the colors are determined is you look at a specific node here, so a specific circle, and you say, what is the distance to your closest neighbor?
Yeah.
And let's say its distance is on our screen 10 pixels, then you give it red. If it's 20 pixels, you give it orange, and so on. Okay. So you have some assignment like that. Then are you saying that consciousness is what takes this set, like I mentioned, there's red, green, orange, and so on. There's a set of colors here. Consciousness is what does the assignment of the colors to the particles?
It assigns the colors in accordance with the as the separations go up. And there is this very striking fact that there is always a hierarchy of separations in all of the ones that come out. And I'm saying that is how color comes into our existence. We can't explain why. I mean, I don't think it will ever be possible to explain why anything exists. But what we can do is to describe it. Let me see if I can find it. Have I got? I read a nice book on consciousness by Christoph Koch.
Mm-hmm.
And he says, what is consciousness? He says it's experience, what we experience. And then he has a nice definition of experience. Can I find it?
Curt here. Several days later, I received an email from Julian, which I'm going to read. Dear Curt, I couldn't find the passage in the book, The Feeling of Life Itself by Christoph. Having said that consciousness is manifested to us as experience, he says that experience has 5 distinct and undeniable properties. Each one exists for itself, is structured, informative, integrated, and definite. I liked that as soon as I read it. and it struck me that it bears a close resemblance to my mathematical notion of shape.
I would say I would encourage everybody to think about what experience is like, and whether, you see, it's not just that motion, all of things like change. I mean, when we listen to music, with the sound change, the quality of the frequency of the things, the sound is changing, the speed, all of that has profoundly influenced the way people trying to understand the world have formed their concepts, and maybe it's deceiving them. Let me say another thing. It's very extraordinary with Maxwell and the electromagnetic field. So, well, first of all, Newton himself was very worried by his theory of gravity because it seemed to allow instantaneous action at a distance. And he said himself that this was, anyone who was trained in philosophical thinking that was something unacceptable. And I recently read a very interesting book about the work of Faraday and Maxwell. And Faraday did it was incredible, marvelous work he did. And he discovered various laws. And on a continental trip, he'd met Ampere in Paris, and they'd become good friends. And Ampere, using Newtonian type action at a distance, had derived mathematical equations which explained all of Faraday's results. Faraday had been hugely impressed. We all know the story of iron filings on a paper above a magnet, and they make these patterns. And that had led Faraday to think of, what did he call it? An electrotonic field or something. But anyway, he had the idea of lines of force. And then Maxwell started giving that mathematical form. And somewhere Maxwell says, Faraday's results can all be explained perfectly well by action at a distance. But I do not like action at a distance. I am going to. So he introduces an electromagnetic field and an ether, which can vibrate and fluctuate, and the energy is conserved. Now, that's very much, if you think about it, how much our experience, our conscious experience. So Aristotle said that there must be a force, the force must act to keep anything moving because of friction. If you stop pushing something, it comes to rest. So then Newton managed to show that was wrong with inertial motion. Once something had got moving, he said in his absolute space, it would go on forever. But to be changed, that required forces, and those forces acted over instantaneously over arbitrary distances. And Newton hated that, and Maxwell hated that. And so he looked for a different explanation. That's what led to the theory of the electromagnetic field. Well, that led to all sorts of problems within 25 years because of all the problems with explaining black body radiation. And there are still, that led on to all the mysteries of quantum mechanics. Now, there's another thing. Before that, in 1854, this was 20 years before before Maxwell, Riemann had developed the theory of arbitrarily curved spaces. And that then became the theory of general relativity. Now, all mathematicians are perfectly happy with the idea of differently curved spaces, and I think that comes. Do you talk about plasticine on the other side of the Atlantic? This stuff that you build with your hands. Is it called plasticine?
Yeah.
So here, look at this creature here. This is from Beatrix Potter's Johnny Town Mouse and Timmy Willie. This is Johnny Town Mouse that my wife molded it with plasticine.
All right.
So this is a shape. You can make it like that, and I think this is why theoretical physicists are perfectly happy with the idea of a curved space. So they start off with flat space, and then they have a torus. What is it? Or a is it a torus on that side? Yeah. Well, you could make a torus with it's all the things you can form with your hand with plasticine, and that makes them perfectly happy with this thing. Now, then the problem starts arising. Which of all these possible spatial structures is the one that's describing the universe? Well, possibly you've just created a monumental problem, and consciousness has misled you into doing that because you've got the idea. So what did Riemann do? He had this idea completely against what Leibniz said. Riemann, first of all, got rid of all variety in the world. All he left was, so to speak, the shape of plasticine, but without any markings on it at all, completely featureless, but shape without feature, without markings. And then he imagined coordinates on it, like stars in the sky, but not real stars like you do see in the sky, but imagined. And then if they're close to each other in terms of infinitesimal distances, then he imagined that you've got Euclidean geometry holding locally. But this was a huge achievement mathematically. It's phenomenal that then that turned into geometry that can be dynamical in general relativity and seems to work very well. But it may all be a colossal invention, and all come because of our feeling that we can hold plasticine or dough. When I bake bread, so I make buns, and I mold with my hands.
Uh-huh.
Maybe just that feeling that consciousness gives us that we can make things of different shape leads theoreticians to use these forms, but then creates all sorts of problems for them. I was talking to a collaborator about this, and I mean, that which shape of the universe are we going to have? But Poincaré, the great mathematician Poincaré, he said, why don't we just stick with with Euclidean geometry? It is so simple, because then he said the instruments, the measuring things that we use to measure geometrical relationships, those are determined by the forces that are acting on the particles in the substance in the thing. So the fact that I've got a ruler here, that ruler has got the shape it has, and it's nice and smooth because of the forces that are holding it together. So maybe geometry comes about, the actual geometry that we measure and experience could be a combination of Euclidean geometry and then the forces that are acting. And then in 1921, Einstein published a paper called Geometry and Experience, and he gives a very nice description of Poincaré's theory, and he says, sub specie aeterni, and Poincaré is correct. Basically, he's right. That is correct. But then Einstein. I'm getting them all muddled now. Einstein was so worried about quantum mechanics and what the real forces were. He says it's too early for us to tell. But maybe maybe Euclidean geometry is all we need. That's what Poincaré conjectured. And if you look at those extraordinary structures that in those images I've shown, and bear in mind that there are probabilities for shapes, that the existence of something like a Born density for shapes is rock solid mathematics.
I'm not understanding. Are you suggesting that our insistence on locality over non-locality is the problem? That we shouldn't be troubled with action at a distance?
I think so, because you see, what is regarded as the greatest I think most people who think about quantum mechanics would say the greatest mystery in quantum mechanics is that entanglement correlations are set up instantaneously between points in space that are arbitrarily far apart. And that's so when Schrödinger back in 1935 coined the expression entanglement in English. There was a German word he'd used before, but he called it entanglement in English. At the end of the second paper, he talks about when he says it's very well confirmed in quantum mechanics in the laboratory, but the speed of light is not coming into play. But he said, I'm not alone, that if these entanglement correlations can be established effectively instantaneously, I will find that repugnant like other people do. And this is the great mystery. But to confirm that these have been established, later on, there must be something like a photograph of a large enough area to show the two places that are correlated all together in a single photograph. So the evidence ultimately is in a photograph, it's in a snapshot. So if you can then explain why that snapshot exists, that there's a high probability for that snapshot, which is a shape, if there's then you've explained the things. So nobody finds the existence. So you take n particles in Euclidean space, there's something like n squared divided by 2 ratios of separations between the two, and they're all correlated. There's colossal correlation between points in Euclidean space. Nobody thinks that's mysterious because they're so used to Euclidean space. But maybe that's what's behind entanglement correlations. Maybe that's what we call entanglement correlations are just reflections of those correlations. It could be as simple as that. It's a possibility. I'm not saying it's right. Nothing is certain. But I think it's a challenge. It's keeping me happy in my old age.
Mm-hmm. How is it you're able to come up with so many ideas at 88? And also stay excited about physics and math.
I guess just I'm a lucky person. You know, I went right back in 1969. I decided to go independent because I wanted to think about time and motion and things, these fundamental things. And I did this incredibly boring job of translating scientific Russian for 28 years.
Yes.
Good money earning, very stable, desperately boring. But then 6 years, in 1974, I got my first paper. It was in Nature, got pretty well received, quite publicized by Nature. And
Congrats.
That brought me my wonderful collaborator, Bruno Bertotti, in Italy. We worked together for about 6 years. And then I felt my pension fund was big enough in 1996, so I retired then. And I've now 29 years. I've had all to myself, and I've had some very, very good collaborators. I was very lucky to meet somebody called Jimmy York, who'd done very important work on general relativity, and he put me on to working with his first PhD student, Nilo Murku, the Irishman in Cork. Both of them sadly died recently. But I collaborated with the Irishman for about 10 years with other students. And then Tim Kozlowski, who's now, I would say, my main collaborator, he's been working with me on and off now since 2008. I met him at the Perimeter Institute. And things are just, more and more things are coming. The real breakthrough came with this alternative explanation of the arrow of time within Newtonian theory. The fact that I came up with that was reading Leibniz. It was over 30 years from leaving. It was 29 years from reading Leibniz to then finding the expression for the variety, and finding that it was already sitting inside Newton's theory of gravity. And then just more and more ideas came, and Tim Kozlowski, the German collaborator, was very important. He was the one who, because I was thinking that because before Manuel had made that remarkable discovery at the observatory in Paris, I had been thinking that the smallest separations would be why the electron doesn't fall to the nucleus in the atom, that would be the thing. But when I discussed that with Tim, he said, no, you should think of it in terms of the Pauli exclusion principle, which applies to fermions, which behave in a quite different way from bosons. Photons behave in a quite different way. So I'm now suspicious whether there are any photons at all, but that the fermions exist, and
interesting.
And that we have an explanation of why they can't all sit on top of each other. It's just that at any given value of the complexity, because that expression, go back and show the expression for the variety on page 1. It's that second factor in the round brackets where the separation's 1 over A plus 1 over B. So if A goes to 0, that immediately becomes infinite. So it's incredibly, I think this is this could be, if we're right, if Tim and I are right, this is the explanation for the stability of matter. You cannot, at a given age we are at a certain age of the universe. That is quite clear. I mean, that I don't think anybody would argue with that. The universe has a certain age. And that means that it has a certain value of its variety. If you go far enough out, you will get a value of the variety, because that's, again, we haven't even looked at the evidence for that. But that's actually, it might be just interesting to look at that. That's page, I think that was page 3? Yes, let's look at page 3. We have looked at that. There's something incredibly special about the two factors that define the variety and are in the Newtonian theory. So the fact that you get this incredibly uniform ball of 5,000 particles, and then on the right, that section through it, which is very, very uniform, but not exactly uniform, that's only possible in 3 dimensions, where you're multiplying a potential which is 1 over R by a quantity which increases as R. So the thing that's under that square root increases as the distance with the distances, and the other one goes as inversely as the distance. And that scale invariant quantity in 3 dimensions. This is related to Newton's potential theorem. Newton was very proud of this theorem, which explains why celestial bodies which are not rotating are perfectly spherical. And it's a unique property of 3 dimensions and that particular combination, 1 upon R multiplied by R, making it scale invariant. That's pretty impressive. So and that satisfies the cosmological principle. The universe looks the same wherever you are. So that's the holy grail of cosmologists, but they struggle to get it. And it's all done with this pretty strange theory of inflation. Roger Penrose thinks inflation is just absolutely mad, crazy. He can't believe it. Now,
I just spoke to Neil Turok, who also is against inflation.
Yeah, there's quite a lot of people. Yeah, Neil is. We were developing precisely that was when Kozlovsky and Flavio Mercati, my 2 main collaborators at the time, were at Perimeter when Neil was the director. And he heard me talk about it, and he liked. In fact, he has a paper out recently which apparently cited our work, or me, I forget exactly. I think he may have cited the Janus point. But that, again, I would say maybe theoreticians are looking, we have this expression to look a gift horse in the mouth. Do you have that across the other side?
No, or maybe we do. I haven't heard it.
Well, it means if you're offered a horse for free, and then you say, I'm going to first look and see if it's got good teeth, then that's thought to be pretty crazy. So it's saying looking at a gift horse in the mouth to check the teeth. But, I just think it's just possible that the whole story is incredibly much simpler than anybody thinks. And that as I was saying, because my wife was able to mold the plasticine into the shape of Johnny Townmouse, but there's also Timmy Willy's up there too.
Okay.
This enables theoreticians to think that three-dimensional space can come in all these incredible different possibilities. I mean, this was the Poincaré conjecture, which wasn't it the Russian who proved it eventually in 3 dimensions, the most difficult one to. I mean, this huge variety of shapes, and then which one is going to be realized in nature? Or maybe all of that's the wrong question. Instead of saying, what can we do with the simplest one of all, and be suspicious about all the others, because it's an experience which consciousness has given. Just because we can mold plasticine to any shape we like doesn't mean to say that's the way the universe is made.
Julian, I'd love to continue to speak with you. I have so many questions, so we'll have to have a part 3. I have questions like, where does spin come from, which I'm sure you can get to next time. And I know that scale invariance in 3 dimensions is broken in the standard model because of masses. So I want to know about how your theory accommodates masses as well. You can feel free to comment on this shortly. But anyhow, I want to talk to you about so many more topics and questions. It'll have to wait until next time. If you want to comment on how masses come about, that's fine. But if you want to save that until next time, and we use this as a teaser for people to salivate at, then
I would say let's stop now, because there's so much work to be done. I would say all that is established so far is certain really big possibilities have been opened up. I think the possibility that there just is no quantum mechanics, it's just probabilities of shapes, has been opened up as a real possibility. That consciousness has misled us into introducing many more possibilities than need be. So that's created work for the theoreticians to see which one might be realized, when in fact the simplest one would have been perfectly good all along. That's all I'll say at the moment. Now, I'm now 88. Whether I'll get much further, we'll see. But if people start doing it, it'll be very interesting to see what Maria in Lisbon finds with her analysis with the supercomputer that she's working on now. Maybe some striking things will come. Maybe somebody watching this will come up with some idea. And I am getting approached. Somebody from India I was talking to yesterday, he's decided to avoid going into academia, avoid the publish or perish syndrome, and he's now starting to study all these ideas in shape dynamics. Maybe he'll come up with something. It's. I think it should be explored. That's the challenge I put out. Is the universe much simpler than people have thought, but nevertheless incredibly rich, thanks to consciousness.
Thank you.
Well, pleasure talking to you, Curt. All right.
I've received several messages, emails, and comments from professors saying that they recommend theories of everything to their students, and that's fantastic. If you're a professor or a lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe Each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gained from rewatching lectures and podcasts. I also read in the comments that, hey, Toll listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.